Memari with a new experiment. Our experiment for today is preparation of dibenzalacetone. This reaction that is used to prepare dibenzalacetone is aldol condensation or cross-aldol condensation. Is a reaction between ketone and the aldehyde in a basic solution. We chose the acetone as our ketone to react with benzaldehyde. Acetone has alpha hydrogens, but our benzaldehyde doesn't have any alpha hydrogen, which is a perfect or better choice of the our carbonyl compound, because if both compounds they have alpha hydrogen, then we could get two enolate ion. For more information, please watch the pre-lab discussion for this experiment. This reaction takes place in alcoholic solution. So the solvent that is used here is alcohol. Sodium hydroxide is needed to remove alpha hydrogen from the acetone in this case, because benzaldehyde doesn't have the alpha hydrogen. The ratio of number of moles of our ketone to the aldehyde, or benzaldehyde specifically in this case, is a 2.2 moles of benzaldehyde to 1 mole of acetone. The reason we are choosing this ratio, which gives basically 0.2 moles extra in ratio of the benzaldehyde, is because benzaldehyde can oxidize over the time. Since benzaldehyde oxidizes and it changes to benzoic acid, that part is not going to be involved in the reaction. So we want to make sure we have enough of the benzaldehyde. We have other ways to do that too. We can purify it right away by distillation. We probably use like a vacuum distillation and just isolate the benzaldehyde from the benzoic acid. Or in this case, based on this procedure, I'm just using extra amount of the benzaldehyde to make sure we have enough. I'm going to make the measurements following the procedure. We are using for the milliliters of the sodium hydroxide. We first measured 40 milliliters of sodium hydroxide. Then add to a 125 Memari flask. We also measure 30 milliliters of 95% ethanol. This is the procedure. So you could look at the numbers in the procedure with 30 milliliters. Place this in the ice bath for 3 minutes. We had the mixture in ice bath for 3 minutes to cool down. So when we are adding acetone, it doesn't evaporate right away. So next step, we are adding our benzaldehyde. The benzaldehyde, the procedure, it gives you the volume of benzaldehyde of 4.9 milliliters. We do the calculation using the density of benzaldehyde, which you could find is a literature value for pure sample is 1.047, and we will just divide the mass by that number to get the volume, which is about 4.7. Now, if it's a 4.7 or 4.75, it's not going to make a huge difference, because first of all, we are using excess compound to protect the oxidation part of this reactant. Second is the excess compound. So if it's excess compound, we can comfortably use a graduate cylinder to measure that. So we are going to measure 4.7 milliliter of the benzaldehyde. Just want to bring it to the volume to make it 4.7 milliliter, and pour that into our solvent mixture that we have. Now, based on the procedure again, we are adding a magnetic stir to it and placed on a stirrer, which is the hot plate with the stirring function for 30 seconds to 1 minute gentle stirring. This is going to make a homogenized solution. Basically, benzaldehyde is going to dissolve in the ethanol that we have in the flask. Just a gentle stirring is good enough. I hope that you could see spinning of the magnet for 30 seconds to 1 minute. On the next step, we are going to measure the mass of acetone. Acetone for this reaction, acetone is the limiting reactant. And because it's the limiting reactant, we are going to measure the mass carefully, and we record the exact mass of the acetone. So I'm going to place the mixture in the flask on the scale and press the tare. Well, I could have measured in a graduate cylinder and then add to that. By the time I measure it, because of the low boiling point of acetone, most of it would evaporate. So to avoid evaporation of the acetone, during measurement, I have a cold solution, and I'm going to add drop by drop of the acetone into the cold solution until it reaches 1.218, and that is given in the procedure. So if the drop that I'm adding is going to pass that number, as long as it's very close to that number, and as long as I have recorded the exact mass, I should be fine for my calculation later for this experiment, or your calculation for the percent yield of this experiment. So it's 0. I'm adding drop by drop until it reaches the desired number. Okay, that's 1.034. Now I have to slow down, adding 1 drop at a time, looking for the number that I want. Okay, I think this is the closest I could get to that number, and I have it as 1.211 a second. To take a picture as well for the record, recorded for the mass of the acetone, and the color is already changing. The product is yellow color, but this reaction takes time. Doesn't need high temperature, but it takes time, and we have to stir it constantly. It takes about 30 minutes. So we are going to leave it on the stirring with the magnetic stirrer, and it will spin for 30 minutes while the product is forming. I see the color change, I see the precipitation, it turned cloudy already, and our product actually is a solid compound. So we're going to pause the recording at this point and come back after the 30 minutes. 30 minutes of stirring of mixture is up. The time is up for 30 minutes mixture. We have plenty of crystals. The powder or the cloudiness, it shows that the crystals have formed. So it's time for vacuum filtration. For the vacuum filtration, we need a pre-weighed paper, filter paper. So let's go ahead and measure the mass of the filter paper with the watch glass right here. So we are using a watch glass with proper size of filter paper. We're going to measure the mass, and the mass is 49.846 grams. I would also take a picture. $49.847 grams. And we place the filter paper inside the Buchner funnel. to cover the openings of the Buchner funnel. We will add some few drops of water to make this stay, the paper to stay still. Now, we are using a vacuum flask attached to a trap. As I have said in the past, the trap is needed here to avoid any water going into our vacuum system, because this is the electronic vacuum pump. And we connect, turn on the vacuum. We're going to pour the mixture over the filter paper. Can add some water for better transfer of the solid. We want to make sure that all the solid is transferred. And before even all the solid was transferred, I added the water just to make sure that I'm going to get most of the extra base or the sodium hydroxide that was mixed with this to be washed away. So I add plenty of water. Washing this precipitate is going to be challenging. It's going to take some time, and we are just going to continue on washing with water. 3-4 times we are going to wash this with water. So each time we're going to use about 50 milliliters of water, measure 50 milliliters of water, and proper technique for washing would be turn off the vacuum for proper technique for washing. Add the washing solution, which in this case is water. Add to the Buchner funnel and let it mix, or kind of the compound, the crystals are soaked in water. As I showed you in the past, when you pour the water, when the vacuum is on, it can pull it down in one area, not the entire sample. We wait for maybe like 30 seconds and turn on the vacuum. 30 seconds to a minute, it doesn't hurt to wait. Turn on the vacuum, remove the water by the filtration, by vacuum filtration. Perfect. We repeat this like 2 more times. While I was transferring the crystals, I added some water. I'm also washing the crystals 3 times, each time with 50 milliliters of water. So I close the vacuum, add water, wait for like maybe 30 seconds to a minute. And with the stirring rod, you can sometimes mix it with the stirring rod also. Just making sure that is going to mix well and wash well. And what is the purpose of this washing? To remove anything that is water soluble, and specifically to remove all of the sodium hydroxide. Continue washing until the solution that is filtered, or the filtrate, is not basic anymore. Now, this is our 3rd time washing with additional 50 milliliters. If I place 50 milliliters more, it might, I don't want it to be filled up for more than 2/3 of the flask. So at this point, I'm going to stop the vacuum, detach the flask, going to detach the flask, pour the liquid into a waste container. and reattach. The purpose of this ironing is to keep the vacuum flask in place, so it's not pulled when I turn on the vacuum, it's not pulled, drop, and break. Okay. Vacuum is off. I add the additional 50 milliliter. This is the third 50 milliliter of water. Mix it with the stirring rod, with the glass rod.